it is my impression that most of you may not be too familiar with electronic systems. My plan is to devote the first lecture to an introduction to the main problems that we are interested in, namely the problems of the metal-insulator transition and complex behavior in various electronic systems. And then in second and third lectures, I will describe the kinds of experiments that we have done to probe the dynamics. In general, when you have an auto-equilibrium system or a glassy system, there are two ways to probe them experimentally. So first you prepare the system in a glassy phase, for example, the rapid cooling. And then one way is to apply some strong perturbation to the system. Not always strong, but for example, you apply perturbation and then you watch how the system relaxes towards equilibrium. And the other way is to measure the fluctuations of some quantity and then you extract information about correlations. So we have done both kinds of experiments, and so I have divided the lectures according to that. So the second one tomorrow will show you how we can measure the relaxations of conductivity after applying some perturbation. And in the third lecture, I will describe the experiments where we measure the fluctuations. This experimental work has focused on two-dimensional systems. So most of the experiments that I will describe will have been done on this system. However, at the end of the third lecture, I will also describe some experiments that were done on other electronic systems, also where fluctuations of conductivity were measured. So in the first lecture, I would like to start it by recognizing that the modern technology is based on our ability to fabricate and design new materials and devices and to change their properties, especially electrical properties, in a controlled way. So what people normally do is they take some insulators and dope them. They introduce atoms of other elements, so they introduce charge carriers, and the materials then become metals and in some cases even superconductors. So understanding of this process of the so-called metal-insulator transition turns out to be a fundamental problem in condensed matter physics. It is also related to the problem of the glassy freezing of charge carriers, or the Coulomb glass. So in the first part of the talk, I will give a brief introduction into these concepts, into the phenomenology, and also introduce the terminology so that tomorrow, the day after tomorrow, you will know what I'm talking about. I will also show you how this is related to the behavior of many other systems. And then I will focus on the metal-insulator transition in two dimensions because that has some additional complications that I will mention. And to show you that two-dimensional systems are not just a theoretical concept, I will show you some practical realizations of 2D systems. And at the end, I will also show the results of some relevant experiments that have been done on 2D systems, just as an introduction to this discussion in lectures 2 and 3. And at the end, I have listed literature, which includes basically some very well-known review papers and textbooks for those of you who may wish to look up some of these topics in more detail. So I'm sure everyone is aware that the modern technology has been undergoing a remarkably rapid development over the last 60 years or so, much more rapid than in previous decades and especially previous centuries. And I think it is safe to say that the birth of modern technology was in 1947 with the invention of the transistor. All computers are made of transistors, and as you very well know, computers are now used everywhere in all areas of life, from more exotic applications such as space travel to everyday gadgets. The question is, how does it all work? Soon after the invention of the transistor, there was the invention of the concept of the integrated fabrication of a whole electrical circuit made of transistors on a single chip. So the computers contain many such integrated circuits, and here are some pictures which are now probably very obsolete. The invention of integrated circuits was also recognized by the Nobel Prize in Physics. The integrated circuits are now the use of integrated circuits has expanded beyond the traditional area of electronics into the areas of mechanics, optics, and also into chemical and biological integrated systems. And in all these different areas, design paradigms, the processes, methods that were developed for these integrated circuits in electronics are being used as a basis for further development, and they are being enhanced and used in these other areas. So what are these transistors that form the basis of this modern technology? Well, basically, transistors are devices that control electrical currents. They can switch the currents on and off. Or the other way of saying this is that they can turn conductors into insulators and vice versa. Transistors are made of semiconductors, typically silicon, also gallium arsenide. And the question is, why semiconductors? Why the modern technology, semiconductor technology and not technology of metals, for example? And to address this question, it is kind of useful to recall a few things from basic solid-state physics. All of you are familiar with good metals such as copper, gold, silver, and also with band insulators such as diamond. Their properties are very well understood. They are indeed textbook knowledge. They are described by the band theory. However, there are many old materials, that is, materials that have been around for a very long time, such as those semiconductors, for example, phosphorus doped silicon, as well as many novel materials, including high-temperature superconductors, the properties of which are not well understood at all. In all these cases, we start with an insulator, we dope it, we introduce charge carriers, and the materials become metals or superconductors. So for the sake of further discussion, I would like to point out that at any finite temperature, any material will have a finite conductivity. Conductivity is usually labeled with sigma because of the thermal excitations. So the true distinction between metals and insulators can be made only at very low temperatures, that is at zero temperature. So in insulators, the conductivity is zero at zero temperature, and in metals, it is not zero. So I would like to kind of recall what we know from the basic solid-state theory, from band theory from the band theory, and this is in metals. Everybody knows that we have a conduction band which is partly filled, so that even at zero temperature there will be a lot of empty states available to the electron, so the conductivity will not be zero. Because of the Pauli principle, the Fermi energy is very large in metals. It's of the order of 1 electron volt. So, in other words, we have one very large characteristic energy in this system. So it is very difficult to change the properties of such a system. You would have to apply very large energy in order to change its properties. And similar situation is found in insulators, where, according to band theory, the valence band is completely filled, conduction band is completely empty, and they are separated by a very large energy gap, typically larger than 5 electron volts. So in order to get conduction in the system, the only way for this to work is for electrons to get excited into the empty states here. But this energy gap is very large, so at zero, of course, at zero temperature, conductivity will be zero. So again, we have a very large characteristic energy scale, and it will be very difficult to change the properties of such a system. So this is why they are not used in technology, except in certain special cases. But instead we use semiconductors, which are really just insulators, except that their energy gap is relatively small. It's less than 1 or 2 electron volts. So that even at room temperature, some electrons will be excited to the conduction band, and there will be, the material will conduct. So now what happens when we dope such a material? When we add some impurities, atoms of another element, we introduce new charge carriers, and because all these states are filled, they have to go somewhere up here. And because this characteristic energy is very small, we have a small number of carriers, we can easily change their properties. So this is why we use semiconductors. And however, it is not... Okay, the question, according to the band theory predicts that this should be a metal, because all these states are filled, these are empty. We introduce new carriers, they have to go here, so we have a partly filled conduction band. So the question is this really true? In other words, is in the zero temperature limit the conductivity finite? Well, let us look at the classic example, which is a phosphorus doped silicon. So So silicon is a group 4 element. It has 4 valence electrons. Phosphorus is a group 5 element. And it's a substitutional impurity, which means that phosphorus replaces atoms of silicon. And 4 its valence electrons fill up the bonds to the neighboring silicon atoms. And the 5th electron excuse me, is weakly bound to this phosphorus atom because phosphorus has one excess positive charge. So this is like a hydrogen atom, except that the radius is much bigger. So when the doping level, when the number of these phosphorus atoms is very low, these electrons are bound to their nuclei, to the phosphorus nuclei, and it appears based on this simple picture that even though we do have a finite concentration of carriers, the conductivity is 0. Obviously, when we increase the doping, these orbitals will start to overlap and the material will conduct, we'll have a metal. So this is all, so this appears to contradict what the band theory predicts, and the way to answer the question is to do the experiments. So what do the experiments say? Well, this has been studied for many decades in those semiconductors, and the experiments say that the conductivity is 0 for a very low level of doping, and you really need to reach certain critical concentration in order to start seeing some conductivity in the 0 temperature limit. Also, at 0 temperature, the conductivity decreases as you approach this metal-insulator transition, decreases in a pound law fashion. In other words, the experiments contradict the prediction of the band theory, and at this point it is important to recall that the band structure calculations are really single electron calculations. They ignore the interactions between electrons, and this is relevant for many materials. So I've already told you one of the things that is missing from the band structure calculations. So recall, yes?
So when you dope phosphorus, what are the energies to ionize the phosphorus?
They're very small.
They're much smaller than 1 Kelvin?
Oh, I don't remember now.
But I'm saying that the vanishing of the conductivity.
Yeah, well, you could imagine that if you apply, even at 0 temperature, if you apply electric field, the electrons will get enough energy to, leave the phosphorus atom. But at this point, I really don't recall. I guess
I'm just saying that if the ionization energy is sufficiently large, if the dopant is sufficiently deep, then at low enough temperatures you would have vanishing conductivity for low dopant.
Oh yes, but again, the only point I was trying to make is that this contradicts what you would expect based on the band theory. Contradicts the naive expectations. So the point is to show that the band theory does not predict really the behavior even of these very well-known materials.
But the band theory says as soon as you begin to dope, the conduction electrons go.
Well, yeah, they have no other place to go, so they have to go to the conduction band. But we know that this is not quite true because, I will mention here in a moment that the new states are being formed actually in the gap below the conduction band. Yes.
So the no density and the no temperature, when you have the carriers, all the carriers are not necessary actually.
So this is
the impurity size.
Yeah. So there is a formation of new localized states. I was going to mention all that later. There is like a tail, new states localized at the bottom of the conduction band.
Actually, if the temperature is not too low, even at the low temperature, but the temperature is not too low, and if you can, and you may be able to consider the phono assistance. If you consider the electrophono,
yes,
you may have a weaker hope. You still have small hope between the states, nuclear states, and then you can have a small conductivity.
Yeah, that's true, and this will all come later, but I did mention at the beginning, this is why I had it before, that at any finite temperature, every material will conduct because of thermal fluctuations, thermally assisted processes, such as that. So this is why I insisted on making a clear distinction between metals and insulators at 0 temperature. So when I say metal or insulator, I mean, okay, I mean that this is what it does at zero temperature. Okay, so the band theory fails. Why does it fail? It ignores two important effects. We have a low concentration of carriers, so in this case the potential energy becomes dominant, and when we have very strong Coulomb repulsion between the electrons, then this will tend to localize the electrons because they repel each other. They want to be as far as possible from each other. Also, in any real material, there is disorder due to presence of impurities, defects, and so on. So there is always some kind of a random potential. So at low densities, the electrons will kind of localize in these potential wells. They will get stuck. So both of these effects lead to the formation of localized states, so that even though we do have carriers, there is no conduction at zero temperature because they're localized. Okay. So the metal-insulator transition, as I said, strictly speaking, takes place at zero temperature. So this is a general phase diagram. This is the temperature. The transition takes place here. This is the reduced density. So this is where the critical concentration is. And the clear distinction, once again, between the insulator and the metal is, strictly speaking, at very low, that is at zero temperature. And you have to go, there is some characteristic energy, some characteristic crossover energy scale, which decreases to zero. In a Pavlov fashion as a function of density as you approach the transition, and below these crossover temperatures, then the insulator will exhibit maybe the kind of process that you mentioned, the temperature dependence characteristic of insulators and the temperature dependence characteristic of metals. And here there is really no clear distinction between the two materials. So this is the experiment here shown. As I said, that this is a continuous, it's a second order phase transition. So close enough to this critical point, you expect to, because the correlation line diverges, you expect that the microscopic details are no longer important. So you expect to see scaling of conductivity. So in other words, for different temperatures and densities, the behavior of conductivity is described essentially by the same function. And this is what the experiments show, that in the zero temperature limit, also the conductivity decreases in a power law fashion. So in general, we expect power law behaviors. Why is this a difficult problem? Well, because for theorists, they cannot use standard methods that are used for other second order phase transitions. There is no broken symmetry. It is not clear what the order parameter should be. There is no small parameter to use for perturbative calculations, and so on. So basically, the standard approaches fail, and this requires the development of new theoretical methods. Now, as if this was not complicated enough, things in reality are even more complicated. I already mentioned that we have Coulomb repulsion in the real system, and it favors the uniform distribution of the electrons because they repel each other. On the other hand, the random potential favors a non-uniform distribution because it's random. So the system, you have these two opposite requirements. You have a competition between these two effects, so there is frustration in the system. In other words, it is impossible to satisfy all these requirements. So what does this mean? This means that usually the system, there is no unique ground state in the system, but rather this leads to the emergence of many metastable states with similar free energy. So this is the behavioral characteristic of glassy systems. So as opposed to a unique ground state, now we have many metastable states with similar energy that are separated with barriers with all kinds of heights. So as a function of time, the system tries to find the equilibrium state, the ground state, but since it does not exist, it keeps on looking. So the electrons for an electronic system will keep rearranging. They will go from one metastable state to another as a function of time. And since some of these barriers are very large, this leads to very slow dynamics. So the system is out of equilibrium, at least on experimental time scales. And for a charged system, this is called Coulomb glass. This is, again, general case for glasses, all kinds of glasses, I think structural glasses, thin glasses, and so on. So the question is whether in this Coulomb glass system, this slow non-equilibrium dynamics exhibits behavior that is similar to the behavior of other glasses, And if it does, whether theorists can develop some unifying ideas and concepts, whether there are some things that are common or universal for all kinds of glasses or not. Also, it is an important question is what is the relevance of this glassy freezing? How is it related to the metal-insulator transition? People have studied a situation when the interactions are very strong, the system electrons are localized. Due to this, they will change the doping, the system undergoes a metal-insulator transition. Similarly, disorder-driven metal-insulator transition has been studied, but now when we have a competition between these two effects, frustration in the system, glassy freezing, how does the metal-insulator transition take place? So these two problems, the metal-insulator transition and charged glasses, are two of the most difficult and most fundamental problems in condensed matter physics. Coulomb glass itself was predicted actually several decades ago. It was expected to take place, to occur in disorder, in systems with very strong disorder. So electrons are localized because of the disorder, but they also have strong Coulomb interactions. And very early on, numerical simulations actually showed the emergence of many metastable states in such a system. So this is why the Coulomb glass was predicted. However, and these people and many others have continued working on this problem theoretically, numerically, ever since. However, there have been very few experimental studies of Coulomb glasses. There were a few early observations of slow relaxations in some semiconductors, granular films. However, these were really not pursued in much detail. Most detailed studies were done on films of indium oxide by the group of three of Yahoo. More recently, similar experiments were done on granular aluminum films. And also over the last several years, my group has done experiments on 2D electron system in silicon, where we have found a number of signature of glassiness, and I will describe these in the remaining two lectures. And also more recently, we have looked at charge dynamics in lightly doped cuprates. So if there is time at the end of the third lecture, I may mention some of that. And the reason why this is relevant can be seen from here. This is the phase diagram for high-temperature superconductors, which more or less describes the current state of knowledge, and it hasn't changed much for the last 20 years. I did not make this. This is a very widely copied. I don't know who made actually this. So in these materials, okay, people start from an insulator again, and they dope it, and the insulator is an antiferromagnet with a very small level of doping, 2 or 3%. The long-range antiferromagnetic order is lost, and then when the doping is only 5 or 6%, the material becomes high-temperature superconductor. So it's a very dramatic change of behavior over a relatively narrow range of doping. Between these two phases, there is a regime that we are actually interested in. Then there is a so-called pseudo-gap region, and there are lots of strange things going on even in the normal state of these materials. Now, here also some analogy to the case of superconductors is that the band theory here also fails. It fails even to predict the behavior of the undoped material, of the parent, so-called parent compound. Because according to the band theory, this should be a metal, but it turns out to be an insulator. And the experiments, the various experiments have shown that this is a so-called multi-insulator. In other words, the holes in this case, the carriers, the holes are localized because of the strong Coulomb repulsion, which is, again, of the order of, I think it's more than 2 electrovolts. So band theory is, again, useless here. And also, there are many experiments that show, over the last several years, using various techniques, the emergence of nanoscale inhomogeneities in a wide range of phase space of these materials. Now, what does this mean? Here is one example before I continue. The inhomogeneities have been seen in all kinds of properties of this system, and here is an example of the charge inhomogeneities, because this is what we are interested in. And these are STM images of one material At low, for 3 different values of doping. At low value of doping, this is an insulator, and then here it's already a superconductor. And the white areas show the charge distribution in this material. So you can see that it is very inhomogeneous. Even when it becomes a superconductor, it is still inhomogeneous. There are still some areas where there is no charge. Also, there are some computer models, appropriate computer models, which show that the charge distribution is inhomogeneous. And this was done by Cynthia and Charles Reichardt. Cynthia is going to be here next week. I think she will be talking about something else, but I'm sure she'll be happy to talk to you about this if anyone is interested. So there is a lot of evidence for charge inhomogeneities, and note that this is a small scale. This is 5 nanometers. So these are inhomogeneities on the nanoscale. And the reason for this is that, yes?
So the charge in the superconductor, how does it exist? I mean, doesn't it break the covalence?
No. I mean, obviously, no, it doesn't. Actually, let's see. I don't have this phase diagram here. I mean, I will have it maybe in the third lecture. Here, what they find is low temperatures. They find the emergence of spin glass phase. Okay, and this spin glass phase actually extends all the way here up to optimal doping. So there is a coexistence between, and it seems that they compete with each other, superconductivity and spin glassiness. So that has been very well established a long time ago. So this is why this phase diagram says messy insulator. So, okay, so because we are talking about charge, the global phase separation here is not possible because the material has to maintain the charge neutrality. So you can have only nanoscopic phase separation. So obviously you can imagine that there are many possible arrangements of these nanoscopic ordered regions that will have comparable, very similar energies.
So could you comment on what exactly is causing the order in these systems? I mean,
what is causing what order?
I mean, you see this clumping and striping order. What exactly is causing that?
Okay, this will come later. It is energetically more favorable for the system to do that. And here you have not only the Coulomb interaction in this order, non-magnetic, but you also have magnetism. You have spins on operators, so there is a competition, between all these, and it's energetically more favorable for holes to clump. Okay. And I will, maybe it's on the next slide. Yes.
Okay.
Okay. I mean, I will be, keep it, but basically there is a competition between, different interactions, so it's just more favorable. Okay. And it can be shown on some simple, models. Okay, so the question here is because there are many possible arrangements of these inhomogeneities with comparable energies, whether this will lead then to the glassy behavior of auto-equilibrium dynamics for the charge. Now this is, as I said, relevant to many other complex materials. And here are just examples of some phase diagrams for manganites and rutinates. Again, this is temperature, this is doping level, and the only reason why I'm showing this is to show you that there are many different phases. And this is because there is competition not only between charge degrees of freedom, there are also spins, lattice structure changes in some cases. So it's really complicated, and this gives rise to inhomogeneities in many cases, and this is, I think, a picture obtained using an optical microscope. So I think it's for this material somewhere, just to show you basically again that we have an inhomogeneous distribution of charge. So a number of people who have been working on these...
I'm curious about the inhomogeneities. Do they exist in the superconductors as well?
Yes, yes.
Present? Okay.
Yeah. I mean, they have been found in the superconducting phase inside as you warm up. So it seems that, there is a competition between the two. Even, so they're really everywhere. So I think everything is glassy. That's my personal opinion.
So it's a competition in the superconducting phase. It's a competition between the energetically favorable repairing and ordering versus the entropic glassiness. Is that the sort of competition you can imagine?
I don't want to make any strong statements about that part of the phase diagram. But yeah, you can.
No, but it's still integration freely. Some of the
Yes.
classing is about the magnetic moments.
Yeah.
This is ordering of the electrons.
Yeah, so, yeah, I do hope that we have time in the third lecture to talk about these two traits a little bit more, because as he said, there is spin glassiness. And then there is also, we think, a charge glassiness due to Coulomb interactions. And we did try to kind of separate the two experimentally, which is not easy, but I hope to show you that. So at this point, I just want to say that there are lots of inhomogeneities everywhere, and the number of people working on these strongly correlated systems have indicated or proposed that exactly because of the competition between many ground states, this competition would give rise to the emergence of some intermediate heterogeneous phases, because the system, the frustration, the system doesn't know what to do, where to go, so it kind of settles for phase separation on nanoscale. So the question is whether this leads to non-trivial out-of-equilibrium dynamics, and also in many cases people, or most cases, are interested in the ground states of the system. So at zero temperature, the quantum effects also have to be taken into account.
For the first diagram, this is the magnet. The material is magnet.
Yes.
For this material interaction, you have the antiferromagnetic phase.
This is ferromagnetic. Ferromagnetic. I really don't know actually which part.
In the first diagram, you type A.
Here. Yes.
This is the antiferromagnetic.
Yes. Okay, yeah, this is antiferromagnetic. Okay, I really don't know much or anything about these materials, except that they are complicated, and I'm not quite sure which part of the phase diagram this corresponds to either. The point was just to show that, in these materials there is a competition between many different ground states, because many effects, degrees of freedom are important, and this leads in general to the emergence of various inhomogeneities. So in general grounds you would expect to see out-of-equilibrium behavior. So that's the point I was trying to make sure.
On the top right, is that a steady state or is that some kind of a transient?
This was done by an optical microscope. Okay, so whatever happens on the time scale, it takes them to take a picture. So in some of these cases, like in STM, for the STM images, it is those measurements or scans are done on a period on the time scale of a few hours. My belief is that at lower temperatures, maybe if they repeated the scan, say a week later, they might see a different charge distribution, because the relaxation times are very long. But this has not been done. Maybe it will be done. But even what these people have done up to now has been extremely challenging technically. So it takes time to do that. Okay, so now I want to focus a little bit on the metal-insulator transition in 2 dimensions and one in 2 dimensions, because for many years it hasn't been clear whether there is really a true metallic state in 2D. And when I say true, again, I mean zero temperature metallic state, and consequently there is a metal-insulator transition at all in 2 dimensions. So why has this been a question? Well, because there were some theoretical arguments that were developed in the 80s, according to which there are no true metallic states or metal-insulator transition in 2D. So let us go quickly and superficially over these arguments. So first of all, we'll look at the case of non-interacting electrons. So we have strong disorder, strong random potential. Electrons get stuck in these localized states, and they conduct according to this thermally assisted tunneling process with the assistance of phonons, as somebody pointed out. There were calculations for the case of the weak disorder, where it was shown that even in this case, because of some quantum interference effects, there will be a correction to the classical Drude conductivity, which at low temperatures will reduce the conductivity. So the conductivity will go to 0. Of course, this was just a first order correction in a perturbative calculation, but nevertheless, people said, okay, this will be also insulating. Then there was work where the effect of weak interactions was included, and it was found that this also reduces the conductivity, also in a way such that conductivity decreases with temperature logarithmically. So, and in the case of strongly interacting electrons with no disorder, we have so-called Wigner crystal. So we have strong flow repulsion. Of course, strong disorder will also make it localized. So the conclusion was in 2D everything is localized. However, in mid-90s, there were a number of experiments that suggested the existence of a two-metal-insulator transition, and I will show you later how they did this. And since that time, this became an active area of research in both theory and experiment. Now, I went over this quickly, but if you were kind of paying attention, I did not mention one possibility here, which is the case of strongly interacting systems with relatively weak disorder. Can in this case strong electron-electron interactions cause delocalization and lead to the metallic phase? Now, as I already mentioned, the earlier calculations of the so-called weak localization were perturbative. So this was just a leading correction. There was some early theory. There was a hint that the 2D method might be possible, but the theory became uncontrolled at low temperatures, which is where it's most important. And actually very recently, only a few years ago, this work was expanded, and they were able to sum all the contributions coming from the interactions and to show that the interaction contribution changes sign and wins over weak localization. In other words, the conductivity as temperature goes to zero, conductivity grows, and you have a metal. So I think the theory now does show that in 2D, in principle, the 2D metallic state is possible, but, there's always a but, unfortunately, this theory probably does not describe experiments, so further work is needed to describe the real world. Okay, so I promised to mention a few practical realizations of 2D systems to show you that this is not just a theoretical concept. One realization are thin films, and of course there is a question. I mean, what does thin mean? How thin is thin? And I know of cases of graduate students who fail to answer this question on their thesis defense, even though they worked on thin film. So what do you think is thin? I mean, is 1 micron thin, 1,000 angstrom? How thin does it have to be thin? 100. Okay, maybe still have time if you're graduate student. Well, this is physics, right? So these words really do not have a meaning unless you compare them to something else, with respect to something else. So it has to be thin enough compared to some relevant length scale. So in case of hopping that you mentioned, there is some characteristic hopping distance. So if the film is thinner than that, then electrons will not be able to hop perpendicular to the thickness. So it has to be thin compared to the relevant length scale. Okay. Then the second example, and the most studied one, is 2D systems is semiconductor catastructures at sufficiently low temperatures. This is what we use. And I will discuss this later in more detail. And then there are also quasi-2D systems, such as these cuprates or high-temperature superconductors. So for some purposes, they look 2D, but they're really quasi-2D. And the reason for that is that their structure, they have layers of copper and oxygen atoms, where it is generally believed the phenomenon of high-temperature superconductivity takes place. The coupling between these planes is strong, and the interplane coupling is very weak, so in some cases they may be considered quasi-2D. Okay, so coming back to the transistors, because this is where our experiments were done. In particular, we looked at the silicon MOSFET, so we are back to those transistors that I mentioned at the beginning. So this is the silicon MOSFET, which forms the basis of semiconductor technology. MOSFET is an abbreviation for metal oxide semiconductor field effect transistor. It is actually easy to remember what it stands for because it describes the structure. On top you have a metallic gate, so this is a metal. Then you have oxide, silicon dioxide, and you have a semiconductor. So this is MOS. And it's a field effect transistor because you apply an electric field to the gate and then you change the current. So the field causes this effect. Okay. So here is another side view of the silicon MOSFET. So at the top again we have this metallic gate. oxide, which is an insulator, and then we have this semiconductor or silicon, and here are the contacts. So when you apply, say, positive voltage to the gate, you are attracting electrons from the bulb or from the contact. They pile up here at the interface, and you have this so-called inversion layer. And the Venn diagram for this structure is shown here. So this is for the gate, for the metal, silicon dioxide, and semiconductor. Now, because you're putting three materials together, the chemical potentials have to be the same in all of them, which leads to the band bending. So basically, these electrons here at the interface live here in this potential well in the conduction bands for sufficiently large gate voltage. And the thickness of this layer is typically 30 to 80 angstrom. So let me blow this up a little bit. So we have electrons in a narrow potential well. So this becomes a problem in quantum mechanics. So their motion perpendicular to this well becomes quantized. So there are discrete, they can only be in discrete energy levels. There are subbands here. And so the energy for electrons in this interface is equal to the energy of the subband plus the energy, kinetic energy for motion parallel to the interface. So basically, if the temperature, this you can see that the subband spacing is not very large. So if the temperature is low enough, electrons cannot get excited to these upper subbands. They have to sit in this ground subband, and they can move therefore only parallel to the interface. So effectively, it's a two-dimensional system. And this is why the experiments also have to be done at low temperatures. Okay, so we have a 2D, two-dimensional free electron gas.
For the real perspective, you should have the spin-out economy.
Excuse me?
For the real situation, you normally should have the spin-out economy.
Okay, there is no spin orbit in silicon. Yeah, so I was just talking about silicon. Yes, things can always get more complicated. Okay, so we have a two-dimensional free electron gas, and it can be found calculated easily that the density of state is a constant. And so this is the effective mass, and this is the spin degeneracy, which is 2. You can each state have spin up and down, and there is also something called valley degeneracy, just because of the band structure of the silicon. It has different values. The conduction band has several values. So this really, in this case, this is 2. In other semiconductors, it might be 1. So the point is, this is all well known, and in fact, these two systems have been studied extensively since late 60s when these people first showed that this was really a two-dimensional system, and it was my privilege as a graduate student to work with 3 of these. Okay, so so this has been studied so much, not only because the physics was interesting, but also because this is the basis of a multi-billion-dollar industry. So a huge number of people has worked on these materials, on these devices, to understand every single aspect of that. From the point of view of physics, interesting effects, integer and fractional monopole effects have been observed in these systems in high enough magnetic fields, and this was recognized with 2 Nobel Prizes in physics. So up to now we have 4 based on transistors. One wonders if there is room for more. This may not necessarily be the case, but really they have been studied so much that really it's a question if one can learn any new physics from these materials. And of course I wouldn't be asking this rhetorical question if the answer was no. I will show you that yes, we can use these systems to learn some new, novel, interesting things. So let me move on with the MOSFET. So I said, okay, the density of state is constant, so this is what it looks like. So this is the bottom of this subband. We'll assume all temperature is low enough. Electrons are 2D. We start filling this up, and this is a constant. So the one reason why these devices are nice for physics, for experiments, is because the carrier concentration can be changed continuously, easily over 2 orders of magnitude, simply by varying the voltage on this gate. So you're just turning the knob and you're changing the density. Now imagine working on doped semiconductors. These people have to use a different sample for each different value of doping. And they can never do it as precisely, and you really cannot do many different densities. So this is one reason why this has been easy to use. Now, just like in any real material, there is always dissolver. So when we add this order, this leads to the formation of these localized states. And just like in semiconductors, the localized states are here in the band tail. So this is what the density of states looks like. In this MOSFET, the disorder comes from sodium ions, which are charged. They are randomly distributed throughout the oxide. So even though they are in the oxide, the electrons are in silicon at the interface. Electrons see this smooth random potential due to these charges. And there is also some surface roughness, but that becomes more relevant at high densities. So we have so the point is electrons move in this random potential in the system, and of course we have to have Coulomb interactions because they're charged. So now I come again to the question of the 2D metal-insulator transition. What do we see if we measure resistivity as a function of temperature in this silicon MOSFET? So these different curves correspond to data for different electron densities, starting from the low density. And you can see that at low densities, resistivity at temperature goes down to 0, increases exponentially. So it exhibits insulating behavior because in the 0 temperature limit it will diverge, the conductivity will be 0. However, at higher densities, which is here, the resistivity actually drops as temperature goes down to 0. So this is metallic behavior, and it's hard to extrapolate to 0 in this case, but if you did, you would end up with a finite value of conductivity. And then there is a density which separates these two types of behaviors, which some people call the separatrix for that reason. Many people thought that maybe this corresponds to the critical density, even though in some cases it is not true in general. I will say more about this tomorrow. And the point is that at some low enough temperature, there is a dramatic change in the behavior. See, these curves, they all go up, and these curves go down for different densities. So somebody asked a question about scaling. The reason, okay, so these curves look similar. So you may imagine that if you shift them this way, they might collapse, and these curves also look similar. If you shift them this way, they might collapse. And the reason for you to try to do this is because this is supposed to be a quantum phase transition. So you want to see whether the conductivity exhibits this scaling that I mentioned earlier that is expected in general case. So this is what these people did. Actually, such measurements have been done many years ago by other people because I said a large number of people studied these systems. However, because of those ideas from the 80s, they did not believe eventually there was a true metal-insulator transition. So Kravchenko and collaborators wanted to provide some evidence for the existence of a true metal-insulator transition, and they decided to attempt scaling. So these are the same data. It's just that this axis is rescale. So what does this mean? It means that for each of these curves, for different densities, they divide temperature by some number until the curve shifts, and so they make all of them collapse. And the number that they use for each curve, to shift each curve, is shown here as a function of density. So you see that on the metallic side and on the insulating side, all data can be described by the same function for different temperatures and densities. And that this characteristic energy scale decreases in a parallel fashion. This is a Lombard scale, so this decreases in a parallel fashion as you approach the critical density.
You have different power of
actually, within the error is the same. And so they demonstrated this scaling, and I'll mention this more on the next slide. They demonstrated this scaling, which is exactly what you expect if you had a true quantum phase transition. However, this because yes.
So when I look at the rescale data, it looks like the resistivity is not going to 0; it's going to some finite value.
Yes.
So
yes. So it's if it keeps doing that, then it means it's metal. I mean, it doesn't have to diverge, then that would be a superconductor. So, yeah. So it's just a metal. So anyway, this was very nice, but because people believed so strongly that there could be no true metallic state in 2D, this was not taken seriously at all by a number of people. And at that point, I remember that as a graduate student, I had some similar data. I mean, I was working on MOSFETs, of course, you measure conductivity as a function of density, temperature, and so on. So I was curious to see whether in our samples we see the same kind of behavior. And I had some samples where we could actually control the type of desolder. So for a certain type of desolder corresponding to this case, we found the scale with the same exponent as Krochenko. So these were totally different devices, and I think it was nice scaling. So at this point, only after this was published, and it's kind of funny because it was published in TRL 10 years after I actually took the data as a graduate student, so don't throw anything away. Okay, so at this point, people finally realized, oh, maybe there is something really going on here. And from that point on, I mean, there was new preprints almost every day, both experimentally and theoretically. So there are all kinds of things going on. So it was kind of interesting. But basically, okay. So let me move on. So what I want to point out now is that the change from the insulating to the metallic behavior occurs at relatively low densities, which are typically of the order 10 to 11 per centimeter squared. And you can estimate the Fermi energy easily. And also, you can estimate the Coulomb energy. We know everything here. So what we see is that the Coulomb energy is much larger than the kinetic energy by at least a factor of 10. In other words, the interactions are very strong. You cannot treat this as a non-interacting or weak interacting system. The interactions have to be taken into account. Also,
So it looks like in your data, I can extrapolate the conductivity goes to 0 as opposed to, because that's just a choice.
This is conductivity.
Yeah, the conductivity, the metallic state goes to.
Yeah, so this goes to, insulating regime to 0, as temperature
in the metallic case
goes to something, okay.
I don't see it.
Because the temperatures were not low enough here. They were lower in the other experiments. But there is always this saturation, actually. Well, I'm glad you're paying attention. Okay. Okay, so the other thing we notice is that the critical conductivity is of the order of E squared over H. And from the root expression in 2D, this tells us that KFL is of the order of 1, where L is the mean-free path, and Kf is the Fermi wave vector. So, in other words, whereas in metallic case, the mean-free path is much larger than the Fermi wavelength, so you have nice waves. So when it gets to here, then obviously the disorder becomes important. So in other words, what we have is a case of strong Coulomb interactions and disorder. This is where the metal-insulator transition takes place. So these effects, I think, have to be taken into account. And I'm getting close to the end. One other experiment I wanted to mention before I talk about glassing tomorrow is actually a local measurement of the charge distribution in a 2D system. These were 2D holes in gallium arsenide. And they found that as they reduce the density, approach the insulating state, they start seeing the development of the inhomogeneities in the charge configuration, spatial inhomogeneities in charge configuration. And the onset of this actually takes place before one gets to that separatrix. So this is, again, I think relevant because it also shows these inhomogeneities. It's kind of similar to those STM studies. So the question is, again, because you have these inhomogeneities, many possible arrangements, whether this would give rise to non-trivial out-of-equilibrium dynamics and charge glassiness. So I think the message that I have for you today is that the metal-insulator transition is a fundamental problem in condensed matter physics. It's of relevance to many interesting, important materials. Basically, the problem that we have is that of a strong interaction, and it's a Coulomb interaction, long-range interaction, which is another complication to theories. And they live in a random potential. So because of the competition of these two effects, one expects frustration in the emergence of dynamic inhomogeneities and glassiness. 2D systems in semiconductors are easy to use. They have the advantages over many glass materials. And now that I worked on cuprates, now I appreciate it much more than ever before. It's a very well-developed technology, so it's really helpful. They're also good because you can control all the relevant parameters easily. You can change their interactions and dissolve them independently by fabricating a different type of a device and so on. And they're also, compared to these other materials, simple because they don't have, there are no magnetic or structural degrees of freedom. So tomorrow, day after tomorrow, then I want to then discuss, show you how we actually studied electron dynamics as we change the density through the metal-insulator transition in these 2D systems. And the goal was to see whether from the dynamics we can see some evidence for the metal-insulator transition, and also to see what we can learn about the metal-insulator transition and Untitled dynamics in general. And as I said, this is a list of the literature. It tells you, what kind of information you can find in these papers and textbooks. So thank you for your attention.
Okay, so quite a few questions. Let's start there.
So, okay, there was a theory about this universal behavior to metal resistivity, right? Or conductivity, that the conductivity goes to some universal value no matter what substance you take. Do you see that? Or
Conductivity goes to universal value in what?
In 2D systems.
In what regime?
In the metallic region, the 2D metal. Instead of having, so basically the curve, instead of falling at different places at low temperature for the same system, was there this Bose metal idea that gave this universal value?
I don't remember. Yeah. I'm not sure. I'm sorry. I'm not sure what you had in mind.
So there's this papers on Bose metal, which is this
idea.
Okay. All nonsense.
There are lots of papers there, lots of theories. Okay, so that's all over.
Okay. So it's nonsense, huh?
Well, after that, many more experiments were done, and now we have a lot of information, which confirms the existence of the transition, but there are a lot of data and results, and none of those theories can explain any of that. So, the time is to, I think, move beyond that and do something else. There were so many that I try to forget all that.
So I have a question. So you get these STM measurements of these inhomogeneities in your system. Have you looked at correlation functions?
Okay, I haven't done those. Other people have done those STMs.
But have they looked at density correlation functions in those inhomogeneities?
I don't think so. I don't think so.
Yeah.
Have you seen a glass transition?
Yes.
So
that will come tomorrow.
Oh, okay.
Yeah.
Just giving hints.
Yeah.
I'm just wondering how that relates to this quantum critical point.
Well, I'll show you.
Okay.
If you can wait till tomorrow.
Okay, I can wait.
Yeah.
So you mentioned the scaling of the conductivity with temperature,
And density.
and every time you mentioned it, you put in quotes dynamical scaling.
Uh-huh.
What's dynamic?
I think it's called this way. I'm told it's called this way because we have a characteristic energy scale that goes to zero, which is a dynamic or something dynamic. Maybe somebody else has a, another answer, but I asked the same question. I asked you the same question, so that's what I was told.
Well, ultimately it's a quantum system. In quantum systems you cannot get rid of your dynamics, it's always there. And so this is like a Fourier space of that, so you see that in the energy or frequency landscape. So these quantum critical phenomena look like classical critical phenomena, but with dynamics in close, which is why the scaling laws always contain little C's and stuff as in dynamic critical phenomena. Okay. Though it's an equilibrium system. Is that confusing or helping?
Well, we expect scaling also at finite temperature, not necessarily in quantum, but here, okay, it's a phase transition, second order, so you have diverging correlation length and diverging characteristic time or relaxation time. And because this is a zero temperature phase transition, you also have quantum mechanics, which means Heisenberg's uncertainty principle. So because you have a diverging time scale, which means you have to have an energy scale which goes to zero.
Further question? Okay. Let's think.